Good morning, champs. In the previous video, we introduced the basic idea of potential flow. We saw that if a flow is incompressible and irrotational, the velocity can be written as the gradient of a potential function, and that this potential satisfies Laplace's equation. In this video, we now introduce the elementary potential flows. Think of these as the building blocks. Later, we will combine them to create much more interesting flow fields. We start with the simplest one, uniform flow. In a uniform flow, the velocity is constant everywhere. The fluid moves with constant speed u in the x direction. So u equals u and v equals 0. From the definition of the velocity potential, u equals the derivative of phi with respect to x. So the derivative of phi with respect to x is u. Integrating gives phi equals u times x. For the stream function, u equals the derivative of psi with respect to y. So the derivative of psi with respect to y is u. Integrating gives psi equals u times y. So for uniform flow, phi equals ux, psi equals uy, and the complex potential is f of z equals uz. The streamlines are given by psi equals constant, which means y equals constant. So the flow consists of horizontal lines. Now we move to source flow. Imagine fluid being injected at a single point. The fluid spreads outward in all directions. This is called a source. Because the geometry is circular, we describe this flow in cylindrical coordinates. The radial velocity is e divided by 2 pi r, and the tangential velocity is 0. This makes sense physically. As the fluid moves away from the source, it spreads over a larger circle, so the velocity decreases with 1 over r. The potential is e over 2 pi times the natural logarithm of r. The stream function is e over 2 pi times theta, and the complex potential is e over 2 pi times log of z. The stream lines are radial lines, and the equipotential lines are circles. If E is negative, the flow reverses and becomes a sink. Now we look at vortex flow. In a vortex, the fluid moves in circles around a point. The tangential velocity is gamma over 2 pi r, and the radial velocity is 0. So again, the velocity decreases with 1 over r, but now the motion is purely rotational. The potential is minus gamma over 2 pi times theta. The stream function is gamma over 2 pi times log of r, and the complex potential is minus I times gamma over 2 pi times log of z. The streamlines are circles around the origin. And here is an important point. Even though the fluid moves in circles, the flow is irrotational everywhere except at the center. So far, all flows we have seen were either uniform, radial, or purely rotational. In the next video, we take the next step. We will introduce flows that already resemble real physical situations, and we will start combining these building blocks.